we go. So now our next problem, we have an airplane 30,000 feet above the ground begins descending at the rate of 2,000 feet per minute. Assume the plane continues at the same rate of descent. The plane's height in minutes above the ground are related to each other. All right, so our important information, it's 30,000 feet above the ground. It is descending at 2,000 feet per minute. Now descending would let us know that that is actually a negative slope because our rate of change is a negative. We are going down, descending. So rate of change, this is a constant rate of change. Keyword here being constant. So descending, that's going to give us a negative rate of change, negative slope. So write equation, model the situation. Again, 30,000 feet, that's going to be our y-intercept. That's our starting point on the graph. So A is writing an equation. I'm going to go ahead and write this as a function notation. So I'm going to do f of x equals. Now I start at 30,000 feet and I'm descending by 2,000 feet per minute. So that would be my x. Now if you ever write function notation, make sure that these variables right here match up. Once again, this is my x, this is f of x, or known as y, but it's function notation. You can rewrite that as f of x equals negative 2,000x. Make sure that the sign stays with the term plus the 30,000. Now B says to find the altitude after 5 minutes. So I'm simply going to substitute in the value of 5 for my x because again, the height depends on the time for this. So my time is my independent, the x value. So 2,000 times 5, and don't forget the negative. Remember, you need to circle them, highlight them, whatever you got to do to make sure you don't drop those negatives. So f of 5 is going to be a negative 10,000 plus 30,000. So now f of 5 would mean that they are at 20,000 feet. So after 5 minutes, it's at 20,000 feet. Now notice this was 2,000 feet per minute. If it was seconds, we'd have to obviously convert. Now again, still dealing with just the first quadrant on this. If I actually drew this out, I know that this would be my time in minutes, and my feet would be here. And starting at the 30,000 feet is where I would begin. And then I would do my constant rate change descending of 2,000 feet per minute. All right, next up. So we are going to graph each of the graph of this here, and we want to write an equation for each of these, A, B, C, and D, from the transformation of the parent function. So this would be our parent, consider our parent function, our initial equation. So we're going to write all of these out, and then we also want to describe the transformation verbally. So this one is y equals f of x, so y equals f of x. So A is the equation. We're actually doing it as f of x, so f of x could equal, and this is an f of x function. So that's what we're looking for. Oops, sorry. So we're actually doing y prime, because this is y equals. Now if I look at this one here, my main vertices are here and here, and up in here. And if you notice that they've translated down to units. So it's f of x minus 2. So this one would be the graph of f of x, oops, forgetting that y equals f of x minus 2 is the graph of y equals f of x. So the graph of the transform function is the graph of this one, the parent, and it's translated down to units. Okay. Now I'm going to look at the second one here, and you can see that this started at 2, this went up to 1, 2, 3, 4, 5, and no horizontal translation. So B is going to be y prime equals f of x plus, it went from 2 up to 1, 2, 3, 5. So it went up 5 units, translate up 5 units. I would say, I'm not going to write out, but I would say the graph of y prime equals f of x plus 3 is the graph of y equals f of x translated up 3 units. So let's look at C. In comparison, this one went up 3, this one went down 2. In comparison, this one right here has translated to the right. And you see it's gone 1, 2, 3 units to the right. So this is right 3. So when I do this one, y prime equals f of x, it's right 3. You think it's positive, but it's actually the negative, minus 3. Now, when we look at this one here, again, that's going to be inside the parentheses because it's a horizontal translation. I would say the graph of y prime equals f of x minus 3 is the graph of y equals f of x, translated right 3 units. So D, you notice that it actually does a diagonal translation. It's going to move to the left 2 units, so it's left 2, and it moves or translates down from here 1, 2, 3 units. So down 3. Okay? So this one I'm going to put down as y prime equals f of left 2, I think negative, but it's actually positive, and then it translates down 3. So when I state this one, it's going to end up being the graph of y prime equals f of x plus 2 minus 3 is the graph of f of x translated left 2 units and down 3 units. And hold right there. Okay, so now we are going to move on to the next one. So this is a little bit hard to see up there, of course, but that's all right. So this one is number 22. And I just want to know which is the graph of negative 2x minus 1 squared plus 1. So if I actually write everything out, I see that the negative is a reflection over the x-axis. Remember that if it is inside of the parentheses, that would be a reflection over the y-axis. The 2 is a vertical stretch by a factor of 2. Has absolutely nothing to do with whether or not it's reflected up or down. The minus 1 right here is a right 1, and then the plus 1 is up 1 unit. Again, it's square, so that means it's a parabola in the shape of a U. My parent function is going to start at 0, 0, 0 squared is 0, 1 squared is 1, and negative 1 squared is 1. So what I have to do is I actually have to reflect it, stretch it by a factor of 2, and then translate right and up. So I'm going to reflect it first. So these values come down here. And basically it's like saying 1 times negative 2. Negative 1 times 2, so now we are translated to the negative 2. Positive 1 times negative 2 makes that reflected and the vertical stretch of 2. So at this point, I'm using these coordinates right here, and now I have to translate them all to the right 1 and up 1. So since I already know it's reflected, I already know that this one is gone and that choice is eliminated. So if I'm going to go to the right and up, negative you think left, which looks like this one, but it's not. My actual answer would be this one right here, C, because we're going to the right and up. All right, so we're going to write the translations of f of x for each graph. So this is my parent function, f of x, y equals f of x. We're going to actually transform them. So I'm going to get my key little points here, and I'm going to move those. You notice here it's at the negative 2, so it goes 1, 2, 3 left, and then it goes all the way down 1, 2. So this is left 3, down 2. I'm just going to go ahead and write all these transformations right now. This one right here, it's on the 1, it's got to get to the 2, positive 2, so it's got to move right 1. And you see that it's at the 3, but it's got to get to the 5. So between 3 to 5 is translating up 2. This one here gets to the -1. If it's the +1, it means we're going left 2. And we're going all the way down to the -2. So 1, 2, 3, 4, that'll end up being down 5. And this last one here, we're starting at the 3, it ends at the 1, so it's going down 1, 2 units. And it's translating to the right 1 unit. It starts at the 1 and it gets to the 2. That's all I need. So right 1 unit. There are no stretches or compressions, so now we can write each of the equations. Y prime, remember that's our transformed, equals f of x. And this one went left 3, I think negative, but it's a +3. Down 2, -2. B, y prime equals f of x, right 1 becomes a -1, up 2, +2. C, y prime equals left 2, f of x +2, down 5, -5. And D, y prime equals f of down 2, right 1, so x -1, -2. All right, let's look at number 24. Given the graph of y equals f of x down here, draw a graph of each of these functions. So I'm going to make this a little bit larger, and I'm just going to draw it on that graph that it's on right there. I'm going to do the first one in blue. You see it's a +2, I think right, but it actually transforms to the left. So we're going to move all the points. I'm going to get some distinct points. Here, definite crosshairs. You never want to use something that's not a definite crosshair, meaning where the units cross and intersect. So I'm going to take this first one, I'm going to move to the left 2. So 1, 2 units, 1, 2, 1, 2, 1, 2, and 1, 2. So this first graph is going to look like this, and that's choice A. Now if I look at B, I've got to go to the right 1 and down 3. And we're going the opposite. And remember, we're doing this because our function is a f of x minus h plus k. Our horizontal movement goes the inverse. Because of that subtraction sign, the vertical goes the same direction as what we believe. So we're going to move this entire function right 1 and down 3. Right 1, 1, 2, down 3. Right 1, 1, 2, 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 3. And that's the transformation of that graph. This is a little helpful guide just for you guys to look at and understand the graph as the picture. Notice this is, again, our starting point. This is a distance thing. So it's not like all this gets added together. This is how far he is away. This is the farthest point that he gets from home, and then he tracks back home. And this is in relation to time, how long he's gone for. You can see that this is a fast rate of change. He's going at a fast pace. Here he kind of slows down. And then all of a sudden coming home, it seems as though he's picking up his speed again for a faster rate of change. Now, you'll never have a negative distance. All it is, or a negative rate of change, it's just a you'll never have a negative distance. He will have a negative rate of change, his slope. This would be a negative, positive, positive. So when we look at this one, every morning Tom walks along a straight road from his home to a bus stop, a distance of 160 meters. The graph shows his journey on one particular day. Describe what may have happened. You should include details like how fast he walked. So when you're looking at these kinds of things, you want to talk about the fact that he started here at home and he was going at a steady rate of change, steady pace. We could do our slope, 100 over 50. So our rate of change here could be 100, rise of 100 over 50. So for this first half, I could say, when I say 100 divided by 50 equals 2. I could say that he was walking at about 2 meters per second when he first started out from home. Then he started to go back towards his house. And at that rate, I'm coming back to his house. This again, watching your units, these are going by 20s. So it's 20, 40, 60. This is a 60. And this is 5, 20. It's distance 20. Okay? So whenever I look at that one, it's 20, 60 divided by 20, which is going to be 3. So he's traveling at 3 meters per second. He's coming back towards his house, so we're not going to really give that a negative slope because he is coming back towards his house. On other graphs, on other basic graphs, that would be a negative slope. The last one, he is traveling away from home again. So he's going from here, 20, 40, 60, 80, 100, 110, divide by 10, 20, 30. So that's about 11/3 meters per second, and that's what he's traveling at that point. So he's picking up speed again. It looks like he's traveling much faster. This is a slower rate of change than this one. So he was walking at a regular steady pace, then when he started coming back home, maybe he forgot something, and then he had picked up his speed. Then he reaches his the destination of meters per of his distance in meters, and it's 160, so he has a constant rate right there. He's not walking, or I'm sorry, he could still not be walking. He is just 160 meters from home. So that one right there has a slope of 0. And he stays 160 meters from home for a good 120, about 20 seconds. Are all sections of the graph realistic? Fully explain your answer. So they could technically be realistic. We are walking 2 meters per second, then the 3 meters per second, coming back, maybe forgot something a little faster, and then 11/3, which 11/3 is a little bit more than 3 meters per second. It's almost 4 meters per second. So you got to pick up the pace. Maybe he starts running. And then he's just steady. He's maybe stopped at this point. He could be stopping and picking up a bus at this point. What does the y-axis represent? Our y-axis is his starting point. That's where he starts from his house. That's at 0, 0. That's his initial everything. That's where he begins. 0 meters from home, no time has passed. All right, following table shows the path of a penny is dropped from a 220-foot building. Which equation fits the data? Now, if you're not sure, we can see they're all squares, so we're pretty good to know that this is obviously going to be a quadratic equation. If you are struggling, you're not sure, remember you can always find your distance between here to see which one's going to work. So if you get your calculator out, and let me get the calculator real quick. Alright, and remember we always want to reset that calculator. Second plus 712 whenever we first start using it again. So we're going to find the rate change between them. 76 minus 156 is going to be a negative 80, and 156 minus 204 is negative 48. So negative 80, negative 48. So if these were equal, that would be a linear equation, and I would know I need a linear representation. Don't know that, it's not going to work. We know we're dealing with quadratic. So we're going to figure out which one fits it down. Now you can just put those in there. Each x, 1, substitute it in for t, and simplify it down. I know this would be negative 16, so I know obviously that's not correct. This one could work because negative 16 plus 220 is going to give me the 204. And so I can look at that and say that's probably my choice. But what we can also do is we can use our calculator. If you recall, you can go to Stat, Edit. Remember that L1 are your X's, L2 are your Y's. We're going to go back to Stat, over to Calc. Now, if you need it to be a linear equation, go to LinReg. This is quadratic, so we're going to go down to quadratic, quad reg. So, we're going to put in our data into our calculator. Stat, Edit, so just hit Enter. L1 are our X's, 1, 2, 3. L2 are the Y's, 204, 156, and 76. Over to Stat, over to Calc. Now I'm going to come down, like I said, to quad reg. Quad reg is what we need for this one because these are quadratics, they're squares. If it was a linear equation, I'd use LinReg. Hit Enter, keep hitting Enter to come down to calculate, and we get our equation. A is negative 16, B is 0, so there is no x, and 220 is a c. So it's negative 16x squared plus 220, and that's correct. Another choice that you can do if you forget how to do stat and you're taking your test, you can put all of these equations into your calculator. Remember, x is here, and we're going to square everything. You can use the square here, or you can use the caret too. So we're going to put all of these in. Now if I hit second graph, I get to a table of values. And I can see which one matches up. I need 204 at 1, 156, and 76. So at 1, that's negative 16. That one is our negative 16. Then we have, whoops, make sure I have all my equations. Oh, I forgot my 220. I was like, that is not right, it's the same thing. All right, so make sure you have all your equations in correctly. Always double check when you do your equations and when you put in your values for stat. One little number off completely changes your answer. So second graph, I'm coming down to the 1. The first thing I should see is a 204. The only one that's got a 204 is the Y2. Now, Y3 is a little close to the 203, so I'm going to check the next number as well. 156, 156, 200. So I know Y2, which was my second equation, would be my answer. All right, so this one here, biologists have observed that the chirping rate of crickets of a certain species appears to be related to temperature. The table shows the chirping rates for various temperatures. Find and graph the regression line. Use the linear regression to estimate the chirping rate at 100 degrees Fahrenheit. All right, so there's a couple different ways that we can do this. We have this one here that we're going to look at, and so I'm going to do this one with the graph. This one I'm going to do as I did with the last one. We're going to find the difference between these to figure out if we have a linear equation or a quadratic equation or a cubic. So to get from 211 to 198 is a difference of 13. Positive 13. 211 minus 198. 198 to 73 is 15. Then we have another 13. Oh, not 13, I'm sorry. To get from 173 to 140. 173 to 140 is going to be, and let me make sure I did that right, it's actually 25. 1230, okay. So 198 to 73 is actually 25. And if it's easier for you, you can just add them up. So 20 to 46 is 26. 46 to 79 is adding 33. 79 to 91 is, what is that, 12? Let's see, 91 to 113. You're looking at that, and that's going to be 9 plus 13 is 22. And 13 to 40 is going to be adding 27, and it's kind of squishy in here. 140 to 73 is 33. So you can go again and try to see if these match up from the distance here. What's really interesting though is that this one's not a constant. So it's not really going to come out. You can already see this is a difference of 7 and that one's a difference of negatives. You can already see that it's going to be just not exactly a quadratic, and it's not linear either. So the other thing that we can do is still use our stat plot. So if I use stat plot, I go into stat, put in all my values. I have 50, 55, 60, 65. Even though I would take these and put them over the x value differences to get my rate of change, it's still not going to come out good. So I need 70, 75, 80, 85, 90. I'm going to come over and put in my L2, my y's. 20, 46. Double check as you're typing them in. Make sure you put them in correctly. 79, 91. 113, 140. Let's see, 173, 198. So I'm not going to put in the last one just to show you, to remind you. If you try to go to stat over to calc and you try to create an equation, it's not going to work. It's going to say mismatch. If you get that, remember the reasoning for that is that your values, your tables don't match up. So I'm going to come down and I see that I'm missing that very last value. And so I need to put 211. All right, so here's what we're going to do. We're going to go into y equals and we're going to actually stat plot. So I'm going to come up, I'm going to hit plot, I'm going to highlight it by hitting enter. Now what I'm going to do is I see that my smallest y value is 20, my largest is 200. So I'm actually going to come to my window. My smallest x value is 50, the largest is 90. So I'm going to make my minimum at about a 40 for my x's, my maximum at 100. Whoops, for my x's. My y's, I'm going to keep the x scale at 1. That means one little unit each time. My minimum, I'm going to make that at 0. For my y's, my maximum, I'm going to make that at maybe 250. Because it does go all the way from 20 to 211. I need a good little expansion. So now when I hit graph, you can see the shape right here. Now, it doesn't look quadratic. It actually looks more linear. So you could reason that this would be actually linear. So when we look at that, I can say, all right, that's what I want to use is linear. You can also go to second catalog and scroll down. I'm going to actually scroll up to it if I can get to it. I have tape coming on this one here. It takes so long on this, but I'm trying to get to that regression. On your handheld ones, you can hold the button down to get to it. You can also do second R, but I can't read up here the letters, so I don't know where they are. And I can't see. Oh, dadgummit. I can't get to it. It's gonna take way too long. But you can scroll through it. Now it's all messing up. Okay. So you can scroll through it and find that regression. But if I look at the graph, I can tell that it's going to be more linear. So I'm just going to go in Stat, over to Calc, and I'm going to create a linear regression. Now, if you actually use your calculator to generate these things, you want to make sure that you put that into your notes. You want to make sure that you write that in it. Yes, I use my calculator to generate this. So this is going to be my equation right here. A is 4.856. I'm going to put 4.86 for my A, so that's y equals 4.86. 4.86 x, because I'm putting my x, we're going to make that x and that y, and then minus 220.96, so 220.97, so minus 220.97. So now we're going to estimate the chirping at a rate of 100 degrees. So 100 is our x, so we substitute 100 in for x, minus 220.97. So I want to know how many chirps the crickets are going to do within whenever the temperature is 100 degrees. So 4.86 times 100 minus 220.97. 265.03, and I'm just going to leave it at 265 chirps. We can't do 0.03 chirps, so we're going to leave it at 265. And we're going to pause.